Tonight, as you settle into the quiet comfort of your bed, take a moment to feel the solid ground beneath you. The floor. The foundation. The earth that holds you safe and still. But here is a beautiful secret that few people ever think about as they drift toward sleep. The ground beneath you is not still at all. It moves. It breathes. It dances in the slowest, most graceful way imaginable. You are resting on the back of a giant. Not a mythical creature from ancient stories, but something far more real and far more wonderful. You are lying on a massive piece of the Earth's crust. A tectonic plate. And right now, as you read these words, that plate is moving. It moves so slowly that you cannot feel it. Slower than your fingernails grow. Slower than a snail crossing a garden path. But it moves with the patience of deep time, carrying you and your house and your entire city on a journey that began millions of years before you were born. Imagine the Earth as a soft-boiled egg. The hard shell on the outside is like our planet's crust. But crack that shell gently, and you will see it breaks into pieces. Large pieces and small pieces, all fitting together like a jigsaw puzzle. These pieces are the tectonic plates. And just like the pieces of a broken eggshell, they can shift and slide against each other. The Earth has about 15 major plates. Some are enormous, like the Pacific plate that stretches across most of the Pacific Ocean. Others are smaller, like puzzle pieces that fit into the spaces between the giants. Each plate is like a slow-moving raft, floating on something much more amazing than water. Deep beneath your feet, far below the basement, far below the deepest wells anyone has ever dug, the Earth becomes hot. So hot that solid rock begins to soften like warm honey. This is the mantle, a thick layer of rock that behaves like a very, very slow liquid. Think of it as the Earth's own personal lava lamp, with currents of hot rock rising and cool rock sinking in an endless, gentle circulation. These currents in the mantle are what move the plates above. Like leaves floating on a slow-moving stream, the continents and ocean floors drift along on these deep currents of stone. The hot rock rises up from deep inside the Earth, spreads out sideways when it reaches the bottom of the crust, then cools and sinks back down again. This creates a conveyor belt of motion that has been running for billions of years. As you lie in bed tonight, you are traveling. Right now. The North American plate, which carries most of the United States and Canada, is sliding northwest at about the same speed your hair grows. That means that by the time you wake up tomorrow morning, you will be in a slightly different place in the universe than you are right now. You will have traveled about as far as the width of a grain of rice. It does not sound like much. But over years and decades and centuries, these tiny movements add up. Over millions of years, they reshape the entire face of our planet. The Atlantic Ocean grows wider every year, pushing Europe and North America further apart. California slowly slides northwest along the San Andreas Fault. The Mediterranean Sea grows smaller as Africa creeps northward toward Europe. India continues its ancient collision with Asia, pushing the Himalayan mountains higher into the sky with each passing century. This movement creates the mountains you see on the horizon. When two plates push against each other, the edge of one plate can buckle and fold upward, creating mountain ranges. The Appalachian Mountains formed this way when ancient continents collided hundreds of millions of years ago. The Rocky Mountains rose when the ocean floor slid beneath the western edge of North America. Sometimes plates pull apart instead of pushing together. When this happens, new ocean floor is born. Hot rock from the mantle rises up to fill the gap, cooling and hardening into fresh seafloor. This is happening right now along the Mid-Atlantic Ridge, an underwater mountain range that runs down the middle of the Atlantic Ocean like the seam on a baseball. And sometimes, plates slide past each other sideways, grinding and scraping in slow motion. This is what happens along the San Andreas Fault in California. The Pacific Plate and the North American Plate are sliding past each other at about the speed of a growing fingernail. Most of the time, this movement is smooth and quiet. But sometimes the plates get stuck, building up pressure until they suddenly slip. When this happens, the ground shakes, and we call it an earthquake. These earthquakes remind us that our planet is alive and active. The Earth beneath our feet is not a dead, solid ball of rock. It is a dynamic, changing world where stone flows like thick liquid over long periods of time, where continents wander like sleepy giants, and where new land is constantly being born while old land disappears back into the depths. As you prepare for sleep, consider this: every mountain, every valley, every coastline on our planet has been shaped by this slow dance of the plates. The very ground that supports your house was once somewhere else entirely. The rocks beneath your town have traveled vast distances, carrying with them the history of ancient seas, forgotten forests, and climates that existed long before humans walked the earth. You are not just lying in bed. You are riding on a piece of the Earth's crust as it continues its journey through deep time. You are part of a story that has been unfolding for billions of years, a story of moving stone and shifting lands and the slow, patient forces that sculpt our world. Tonight, as you close your eyes and feel the solid comfort of the ground beneath you, remember that this solid ground is actually liquid over long enough time. It flows like a river, but a river that takes millions of years to change course. But what happens when a world stops moving? What becomes of a planet where the stone grows cold and still, where the dance of the plates comes to an end? Deep beneath the ocean waves, in the darkest places where sunlight has never touched, something magical is happening. The Earth is creating new land. Right now. At this very moment. You cannot see it from your bed, but far below the surface of the Atlantic Ocean, a mountain range stretches for thousands of miles. This underwater mountain chain is called the Mid-Atlantic Ridge. It runs down the center of the Atlantic like a giant seam, splitting the ocean floor in two. Along this ridge, the Earth opens up. Not like a sudden crack or a violent tear, but slowly and gently, like a flower blooming in slow motion. The ocean floor spreads apart at the speed of a growing fingernail. And as it spreads, something wonderful happens. Hot rock from deep inside the Earth rises up through the opening. This rock is so hot that it glows like the coals in a fireplace. It flows like thick syrup, like honey warmed by the sun. This liquid rock is called magma when it flows beneath the surface, and lava when it reaches the seafloor. Picture this: miles beneath the ocean, where the water is cold and dark, rivers of glowing rock pour out of the earth. The moment this liquid fire touches the icy seawater, it begins to cool and harden. Steam rises in great billowing clouds. The rock turns from bright orange to dark gray, then to black. Layer by layer, these cooling flows of lava build new ocean floor. Each flow adds another stripe to the seafloor, like adding another ring to a tree. The newest rock forms right along the ridge where the lava emerges. The older rock gets pushed away on both sides, carried along by the moving seafloor. This is how the Atlantic Ocean grows wider every year. The seafloor acts like a giant conveyor belt, carrying the continents of Europe and Africa away from North and South America. The Atlantic Ocean that exists today did not exist 200 million years ago. Back then, all the continents were pressed together in one massive supercontinent. But the Earth's inner fire had other plans. Deep currents of hot rock began to rise beneath that supercontinent. The rising heat weakened the land above. Cracks appeared. The cracks widened. And eventually, the supercontinent split apart like a piece of bread being torn in half. At first, there was just a narrow valley where the land had pulled apart. Rivers flowed into this valley, creating lakes. Over millions of years, as the land continued to separate, the valley grew deeper and wider. Eventually, the ocean rushed in, creating a new sea. That new sea kept growing. The seafloor kept spreading. More and more liquid rock poured out of the Earth's depths, cooling into fresh ocean floor. What had once been a narrow valley became a wide ocean basin. The rock that forms from this underwater lava is called basalt. It is dark and fine-grained, different from the granite that makes up most of the continents. Basalt is the ocean's signature rock, the stone that writes the story of seafloor spreading across the bottom of every ocean on Earth. Scientists have learned to read this story written in stone. They have discovered that the seafloor keeps a record of Earth's magnetic field. As each new stripe of basalt cools and hardens, it locks in the direction of the Earth's magnetic field at that moment in time. Over millions of years, the Earth's magnetic field has flipped many times. The North Magnetic Pole has become the South Magnetic Pole, and the South has become the North. Each time this happens, the new rock forming at the ridge captures this change. The result is a stripe pattern on the ocean floor, like a barcode that tells the story of magnetic reversals and seafloor spreading. This discovery helped scientists understand that the ocean floors are young compared to the continents. While some rocks on land are billions of years old, the oldest ocean floor is only about 200 million years old. This is because ocean floor is constantly being recycled. New seafloor forms at the ridges, spreads outward, and eventually disappears back into the Earth's depths at deep ocean trenches. The process works like a cosmic recycling system. Hot rock rises, cools, spreads, travels across the ocean basin for millions of years, then sinks back down into the Earth's interior to be heated and melted again. The atoms in the rocks are eternal, but the seafloor itself is constantly renewed. As you rest tonight, imagine this slow but constant creation happening beneath the waves. Picture the glowing rivers of liquid rock flowing out of the Earth's heart. See the new land being born in darkness, cooling and hardening into solid stone that will carry the history of this moment for millions of years to come. This birth of new seafloor happens in silence and darkness, witnessed only by the strange creatures that live in the deep ocean. Yet it is one of the most important processes shaping our planet. Without seafloor spreading, the continents would never have separated. The Atlantic Ocean would not exist. The face of our world would be completely different. The Earth breathes through these underwater ridges. It releases its inner heat and pressure through these gentle flows of lava. It grows new skin to replace what has been worn away by time and weather. It writes its autobiography in stone, one cooling lava flow at a time. But this story of creation and renewal is not just about new rock forming on the ocean floor. It is part of a much larger cycle, a dance between creation and destruction that has shaped our planet for billions of years. To understand this dance, we must travel back in time and see how the pieces of our world once fit together in a very different pattern. Long ago, before there were people to name the continents, before there were dinosaurs to walk upon them, all the land on Earth was joined together. Imagine taking a map of the world and pushing all the continents together like puzzle pieces. Push Africa against South America. Slide North America next to Europe. Tuck Australia against Antarctica. Press India into the side of Africa. When you do this, something beautiful happens. The continents fit together almost perfectly. The bulge of eastern South America nestles into the curve of western Africa like two pieces of the same ancient whole. The mountains of one continent line up with the mountains of another. The rocks match. The fossils match. Even the patterns of ancient glacier carved into the stone tell the same story. This matching is not an accident. 300 million years ago, there really was just one giant continent. Scientists call it Pangaea, which means all lands in ancient Greek. Pangaea was surrounded by a single vast ocean called Panthalassa, meaning all seas. Picture this ancient world. One enormous landmass stretching from what would become the North Pole to what would become the South Pole. No Atlantic Ocean. No separate continents. Just one supercontinent under one sky, with one coastline that wrapped around nearly half the planet. But Pangaea was not the first supercontinent, and it would not be the last. The Earth has a rhythm, a slow heartbeat that brings the continents together and then pulls them apart again. This cycle takes hundreds of millions of years to complete. It is called the supercontinent cycle, and it has been repeating for billions of years. Before Pangaea, there was another supercontinent called Rodinia. Before Rodinia, there was Columbia. Each one formed when the moving pieces of the Earth's crust slowly drifted together over vast periods of time. Each one eventually broke apart when deep currents of hot rock in the Earth's mantle changed direction and began pulling the land in different directions. The breakup of Pangaea began about 200 million years ago. It started slowly, the way many great changes do. Deep beneath the supercontinent, currents of hot rock began to rise. These currents heated the bottom of the continent from below, causing it to swell and stretch like warm taffy. Eventually, the stretching became too much. Cracks appeared in the heart of Pangaea. These were not sudden breaks, but gradual splits that took millions of years to widen. Rain fell into the cracks, creating rivers that flowed toward the center of the continent. Over time, these rivers carved deep valleys where the land was pulling apart. The first major split separated what would become North America and Europe from what would become South America and Africa. A narrow sea formed between them, growing wider and deeper as the seafloor spread, and new ocean crust formed along the ridge between the separating landmasses. As the Atlantic Ocean opened, other pieces of Pangaea began their own slow journeys. India, which had been nestled against the eastern side of Africa, broke away and began a long voyage northward toward Asia. Australia separated from Antarctica and drifted toward the equator. The Mediterranean Sea began to form as Africa slowly rotated away from Europe. Each piece of the ancient supercontinent carried with it the memory of their time together. The rocks tell this story. In the mountains of Scotland, you can find the same types of rock that exist in the mountains of eastern North America. They formed as one mountain range when the continents were joined. When Pangaea split apart, the mountain range was torn in half, leaving pieces on both sides of the new Atlantic Ocean. The fossils tell the story too. Scientists have found identical fossils of ancient plants and animals on continents that are now separated by thousands of miles of ocean. Fossils of the same small reptile called Mesosaurus have been found in both Brazil and South Africa. Fossils of the same seed fern plant exist in Antarctica, Australia, India, and South America. These matching fossils were one of the first clues that the continents had once been connected. How else could the same species exist on different continents separated by vast oceans, unless those continents had once been part of the same landmass? The climate tells the story as well. Scientists have found evidence of ancient glacier in places that are now near the equator, like Central Africa and South America. They have found coal deposits, which form in warm swamps, in places that are now near the poles, like Antarctica. This only makes sense if the continents were once in different positions on the globe. As you lie in your bed tonight, you are resting on a piece of this ancient story. The ground beneath you has traveled vast distances over deep time. If you live in North America, your land has drifted thousands of miles from where it was when Pangaea existed. If you live in Australia, your continent has wandered across half the globe since it broke away from Antarctica. The journey is not over. The continents continue their slow dance across the Earth's surface. Africa is still moving north, slowly closing the Mediterranean Sea. Australia is drifting northeast toward Asia. In 50 million years, the Mediterranean will be gone, squeezed out of existence as Africa collides with Europe. In 200 million years, the Atlantic Ocean may begin to close as the continents start drifting back together again. This is the rhythm of deep time. The continents separate and wander for hundreds of millions of years, then slowly begin the long journey home. Eventually, they will come together again to form a new supercontinent. The children of that far future will look at maps showing all the land joined together, just as we look at maps of ancient Pangaea. The dance of the continents is powered by the heat deep inside our planet. This heat comes from the radioactive decay of elements in the Earth's core and mantle. It is the leftover warmth from the violent collisions that formed our planet 4.5 billion years ago. This ancient energy still moves the stone beneath your feet, still shapes the face of our world. But what happens when that inner fire begins to cool? What becomes of a world where the engine of plate tectonics slows and eventually stops? To understand this, we must journey deep into the Earth's interior, to the furnace that drives all this magnificent motion. To understand why the Earth moves, you must journey downward. Not just through the basement floor beneath your house, not just through the soil and bedrock below your town, but down through miles and miles of stone, deeper than any human has ever traveled, into the secret chambers of our planet's heart. Imagine taking that journey now, as you rest in the quiet comfort of your bed. Picture yourself sinking slowly through the solid ground beneath you, passing through layer after layer of the Earth's interior, like a gentle elevator descending through the floors of the tallest building ever imagined. The first part of your journey takes you through the crust, the thin outer shell of our planet. This crust is like the skin of an apple compared to the whole fruit. On land, it stretches down about 25 miles. Under the oceans, it is much thinner, only about 5 miles deep. The crust is made of solid rock, the granite and basalt that form the foundation of continents and ocean floors. But as you continue your descent, the rock around you begins to change. The temperature rises. The pressure increases. You are entering the mantle, a thick layer of rock that makes up most of our planet's interior. The mantle stretches from the bottom of the crust all the way down to nearly 1,800 miles below the surface. Here in the mantle, something wonderful and strange happens. The rock is still rock, made of the same minerals you might find on the surface. But the heat and pressure are so intense that the solid stone begins to behave like a very thick liquid. Think of warm honey or thick syrup. The rock can flow and move, but so slowly that it would take thousands of years to see any motion with your eyes. This flowing rock moves in great currents, like the currents in an ocean, but an ocean made of liquid stone. Hot rock rises from the deep interior, carrying heat from the Earth's core toward the surface. When this hot rock reaches the top of the mantle, it spreads out sideways, cools, and then sinks back down again. This creates giant circulation patterns called convection currents. Picture the largest lava lamp you can imagine, thousands of miles tall, filled with glowing liquid rock instead of colored wax. The heat at the bottom causes the rock to become lighter and rise. As it rises, it cools and becomes denser, eventually sinking back down. This creates a slow, rhythmic circulation that has been going on for billions of years. These convection currents in the mantle are what drive the movement of tectonic plates on the surface. The rising currents push up against the bottom of the crust, creating the underwater mountain ridges where new ocean floor is born. The sinking currents pull the crust downward, creating the deep trenches where old ocean floor disappears back into the Earth's interior. The energy for all this motion comes from heat. But where does this heat come from? Some of it is leftover warmth from the Earth's formation 4.5 billion years ago. When our planet first formed from the collision of countless smaller rocks and debris, all that impact energy was converted to heat. The Earth was once completely molten, a ball of liquid rock glowing like a small star. Over billions of years, the surface cooled and hardened into a solid crust. But deep inside, much of that original heat remains trapped. The Earth is like a giant stone that was once heated in a cosmic furnace and is still slowly cooling down. But there is another source of heat that keeps our planet's interior warm. Deep in the Earth's core and mantle, radioactive elements are constantly decaying. Elements like uranium, thorium, and potassium break down over time, releasing energy in the process. This radioactive decay has been generating heat inside our planet for billions of years, and it will continue for billions more. As you continue your imaginary descent, you would eventually reach the core, the heart of our planet. The core is divided into two parts. The outer core, starting about 1,800 miles below the surface, is made of liquid iron and nickel. It is so hot here that these metals flow like water, creating currents that generate the Earth's magnetic field. At the very center, about 4,000 miles below your feet, lies the inner core. Here, the pressure is so immense that the iron is squeezed back into solid form, despite temperatures that reach nearly 10,000 degrees Fahrenheit. This solid iron ball, about the size of the moon, spins slowly within the liquid outer core, like a planet within a planet. The heat from this core is what drives everything above it. The convection currents in the mantle. The movement of tectonic plates. The creation of new ocean floor and the recycling of old crust. The building of mountains and the opening of ocean basins. All of it powered by the ancient heat of our planet's formation and the ongoing energy of radioactive decay. This is why Earth is a living, dynamic world. The heat engine deep inside our planet never stops running. It has been operating for billions of years, constantly reshaping the surface, constantly renewing the crust, constantly moving the continents in their slow dance across the globe. But not all planets have such active interiors. Size matters when it comes to planetary heat engines. Smaller planets cool down faster than larger ones. They lose their internal heat more quickly, and eventually, their engines shut down. When that happens, the planet becomes geologically dead. The plates stop moving. The surface becomes frozen in time. Mars is one of these worlds. Our red neighbor in the solar system was once more active, with moving plates and flowing lava. But Mars is much smaller than Earth. Its interior cooled down faster. Its heat engine gradually slowed and eventually stopped running altogether. Tonight, as you drift toward sleep, remember that you are resting on the surface of a world that is very much alive. Deep beneath you, ancient heat still flows through rivers of liquid stone. The heart of our planet still beats with the rhythm of convection currents that have been circulating for eons. But what would happen if that heart grew cold, as it has on Mars? What would our world look like if the engine room deep below fell silent and still? Tonight, step outside in your imagination and look up at the sky. Find that small red dot hanging among the stars. That distant point of rusty light is Mars, our planetary neighbor, a world that holds the secrets of what happens when a planet's heart grows cold. Mars is smaller than Earth. If Earth were a basketball, Mars would be a softball sitting beside it. This difference in size tells a story of two very different destinies. Size, as it turns out, determines how long a planet can keep its inner fires burning. When Mars first formed, 4.5 billion years ago, it was a more active world. Its interior was hot, filled with the same kind of energy that still drives our Earth today. Molten rock flowed through its mantle. Heat rose from its core. The surface moved and changed, shaped by forces rising from deep within. Evidence of this ancient activity still marks the Martian landscape. The largest volcano in our solar system, Olympus Mons, rises from the red plains of Mars like a sleeping giant. This massive mountain stretches 13 miles high, nearly 3 times taller than Mount Everest. Its base is so wide that you could fit the entire state of Arizona on top of it. But Olympus Mons is silent now. It has been silent for millions of years. No lava flows from its ancient vents. No new rock is added to its slopes. It stands as a monument to a more active time, when Mars still had the heat and energy to build such mighty structures. Across the Martian surface, you can see other signs of this lost vitality. Great canyons cut deep into the red rock, carved by processes that no longer operate. Ancient riverbeds wind across the landscape, dry channels that once carried flowing water under a thicker atmosphere. The northern and southern hemispheres of Mars show dramatically different terrain, suggesting that some great process once reshaped half the planet. But all of this activity stopped long ago. The reason lies in Mars' smaller size. A smaller planet has less mass, which means less gravity to hold onto its internal heat. It also has more surface area relative to its volume, which means heat can escape more easily into the cold of space. Think of 2 ovens cooling down after baking. A large oven stays warm much longer than a small one. The large oven has more heat trapped inside and fewer surfaces for that heat to escape through. The small oven cools quickly because it has less heat to begin with and more ways for that heat to leak away. This is what happened to Mars. Its smaller size meant it lost its internal heat much faster than Earth. The convection currents in its mantle slowed down. The flow of molten rock became sluggish, then stopped altogether. Without these deep currents to drive surface motion, the Martian crust became locked in place. On Earth, our tectonic plates are constantly moving, constantly recycling old crust and creating new surface material. This process keeps our planet's face young and active. The oldest rocks on Earth's surface are only about 4 billion years old, even though our planet is 4.5 billion years old. The rest have been recycled back into the mantle and reformed into new rock. But on Mars, there is no recycling. The crust formed early in the planet's history and then stayed put. Much of the Martian surface is incredibly ancient, preserving features that are billions of years old. The planet became a museum of its own early history, frozen in time when its geological engine shut down. This stillness has profound consequences. Without moving plates to regulate the planet's climate, Mars could not maintain the thick atmosphere it once possessed. On Earth, our moving crust helps control the amount of carbon dioxide in the atmosphere through a process called the carbon cycle. Volcanoes release carbon dioxide, while weathering rocks absorb it. The balance between these processes helps keep our climate stable. On Mars, when the volcanoes fell silent and the crust stopped moving, this regulation system broke down. The thin atmosphere we see today is just a whisper of what once existed. Most of it has leaked away into space over billions of years, leaving behind a world where water cannot exist as a liquid on the surface. The silence of Mars extends beyond its geology. Without a moving molten core to generate electrical currents, Mars lost its magnetic field billions of years ago. On Earth, our magnetic field acts like an invisible shield, protecting us from the harmful solar wind that streams out from the Sun. Mars has no such protection. The solar wind strips away its atmosphere bit by bit, year after year. Yet even in its stillness, Mars tells us important truths about planetary life and death. It shows us what Earth might become in the distant future, when our own planet's heat engine finally winds down. It reminds us that geological activity is not guaranteed forever, that the forces that shape our world today are powered by a finite source of energy. Scientists study Mars not just to understand our neighbor, but to better understand our own planet. By examining a world where tectonic activity has stopped, we learn more about how and why it continues on Earth. Mars serves as a natural experiment, showing us what happens when the variables that drive planetary geology change. The red color that gives Mars its distinctive appearance comes from iron oxide, or rust, in its soil and rocks. This rust tells another story of a world that once had more water and a more active atmosphere. The iron in Martian rocks reacted with oxygen and water long ago, creating the rusty coating we see today. It is like finding old rust in a garage and knowing that water once flowed there. As you prepare for sleep tonight, think about this quiet world hanging in the darkness above. Mars holds the memory of ancient rivers and active volcanoes, of a time when it might have been more like our own living Earth. Its silence teaches us to appreciate the ongoing symphony of geological forces that still play beneath our feet. But Mars may not remain silent forever. In the imagination of scientists and dreamers, there are ways that a sleeping planet might someday wake again. The question that dances at the edge of possibility is this: could human ingenuity find a way to restart the heart of a world? As you lie in your bed tonight, you are surrounded by something you cannot see, cannot touch, cannot hear. Yet this invisible presence is one of the reasons life exists on Earth. It wraps around our entire planet like a gentle, protective blanket. It is Earth's magnetic field. This magnetic field begins deep in our planet's core, nearly 4,000 miles beneath your feet. Remember that journey to the Earth center we took earlier? At the very heart of our planet lies a solid ball of iron, surrounded by an ocean of liquid iron and nickel. This liquid metal is incredibly hot, thousands of degrees hotter than the surface of the Sun. But the liquid iron does not just sit still. It moves in great currents, stirred by the rotation of our planet and the heat rising from the solid core below. These currents of flowing metal act like the wires in a giant electric generator, creating electrical currents that produce our planet's magnetic field. Picture Earth as an enormous magnet, with invisible lines of force streaming out from the South Pole, arcing high above the planet, and flowing back down into the North Pole. These magnetic field lines create a protective bubble around our world, extending far out into space. Scientists call this protective region the magnetosphere. Most of the time, you cannot feel this magnetic field at all. It is too weak to move your body or the objects around you. But sometimes, in the far north or far south, you can actually see it working. The aurora borealis, or northern lights, appears when particles from the Sun interact with our magnetic field high in the atmosphere. The field guides these particles toward the poles, where they create shimmering curtains of green, blue, and red light dancing across the night sky. But the magnetic field does much more than create beautiful lights. It serves as Earth's invisible shield against the constant storm of particles streaming from the Sun. This solar wind carries electrically charged particles racing through space at incredible speeds. Without our magnetic field to deflect them, these particles would strip away our atmosphere, molecule by molecule, over millions of years. The magnetic field acts like the force field in a science fiction movie, but it is completely real. When the solar wind encounters our magnetosphere, most of it is deflected away from Earth, flowing around our protective bubble like water flowing around a rock in a stream. Some particles do make it through, but they are guided toward the poles, where they create the auroras instead of harming life on the surface. This protection is not perfect. Sometimes the sun releases enormous bursts of particles called solar storms. These storms can overwhelm our magnetic field temporarily, causing problems with satellites, radio communications, and power grids. But even during these intense solar events, our magnetic shield prevents most of the harmful particles from reaching the surface where we live. Mars tells a different story. Our red neighbor once had a magnetic field too, generated by currents in its own molten core. But as Mars cooled down, its core solidified, and the currents that created the magnetic field gradually stopped flowing. Today, Mars has only tiny patches of magnetism in some of its ancient rocks, like fading memories of its once protective field. Without its magnetic shield, Mars became vulnerable to the solar wind. Over billions of years, this constant stream of particles has been slowly stripping away the Martian atmosphere. What was once a thicker atmosphere that could support liquid water on the surface has been reduced to the thin, cold atmosphere we observe today. Scientists estimate that Mars has lost most of its original atmosphere to space. The water that once flowed in ancient rivers and filled early oceans has largely been lost as well, carried away by the same solar wind that our magnetic field deflects. This is one reason why Mars transformed from a potentially habitable world into the cold, dry desert we see today. The difference between Earth and Mars reminds us how important our magnetic field really is. This invisible shield has been protecting our planet for billions of years, allowing our atmosphere to remain thick enough to support liquid water and life. Without it, Earth might have suffered the same fate as Mars. Our magnetic field is not constant. It fluctuates and changes over time. Sometimes it grows stronger, sometimes weaker. The magnetic poles even flip positions every few 100,000 years, with the north magnetic pole becoming the south magnetic pole and vice versa. During these reversals, the field becomes very weak for a short time, but it always recovers. Scientists study these magnetic reversals by examining ancient lava flows. When molten rock cools and hardens, the magnetic minerals in the rock align with Earth's magnetic field at that moment, like tiny compass needles frozen in stone. By studying rocks of different ages, scientists can read the history of our planet's magnetic field stretching back millions of years. The strength and direction of Earth's magnetic field also provide clues about what is happening deep in our planet's core. Changes in the magnetic field tell us about changes in the flow of liquid metal far below the surface. In a way, the magnetic field is like Earth's pulse, revealing the health and activity of our planet's hidden heart. As you rest tonight, remember that you are cradled not just by the solid ground beneath you, but by invisible forces that extend far into space. Earth's magnetic field surrounds you like a protective cocoon, deflecting cosmic dangers that you never see or feel. This shield has been guarding our world since long before life began, and it continues its silent watch while you sleep. But what would happen if we could somehow restore this protective embrace to a world that has lost it? Could we rebuild the invisible shields that once protected Mars, giving it back the defense it needs to hold onto an atmosphere? Close your eyes and imagine standing on the surface of Mars. The sky above you glows a butterscotch color during the day, fading to deep blue at sunset. The air is so thin you could not breathe it. The temperature is colder than the coldest winter day you have ever experienced. But perhaps the most striking thing about Mars is something you cannot see or touch. It is the profound silence of a world that has stopped moving. On Earth, our planet never truly rests. Even when you cannot feel it, the ground beneath your feet is constantly in motion. Tectonic plates slide past each other with grinding whispers. Magma moves through hidden chambers deep below. The Earth breathes through tiny tremors and shifts that happen every moment of every day. If you place the most sensitive earthquake detectors on Mars, they would record almost nothing. The planet that once shook with volcanic eruptions and shifting crust now sits as still as a sleeping giant that will never wake. This silence tells the story of a world where the engines of geological change have fallen quiet. Mars is covered with the evidence of its more active past. Olympus Mons, the largest volcano in our solar system, rises from the Martian plains like a massive sleeping mountain. This giant volcano is so tall that if you stood at its base, you could not see the top even on the clearest day. It would disappear into the thin Martian atmosphere above you. But Olympus Mons has been silent for millions of years. No molten rock flows from its ancient vents. No new lava adds to its already enormous bulk. The volcano that once grew by constant eruption now stands frozen in time, a monument to the geological forces that shaped Mars in its youth. Across the Martian surface, you can see other sleeping volcanoes. The Tharsis region contains several massive volcanic peaks, each one larger than any volcano on Earth. These giants were built by the same processes that create volcanoes on our planet, but they grew much larger because Mars lacks the moving plates that would have carried them away from their underground sources of magma. On Earth, volcanoes like those in Hawaii are carried away from their magma sources by the movement of tectonic plates. This is why we have chains of volcanic islands, each one representing a different time when the plate passed over a hot spot in the mantle. But on Mars, with no moving plates, volcanoes could stay in one place for millions of years, growing larger and larger as they erupted again and again from the same spot. The result is a landscape dotted with these enormous, ancient volcanoes. They stand like sleeping gods across the Martian plains, their slopes carved by wind and dust storms but no longer shaped by the fire from within. Each one tells the story of a time when Mars was geologically alive, when molten rock flowed and the planet's surface changed and grew. But perhaps the most dramatic evidence of Mars' geological death lies in its Great Canyon system, Valles Marineris. This enormous crack in the Martian surface stretches for over 2,000 miles, longer than the entire United States is wide. In some places, it yawns more than 4 miles deep. Valles Marineris was not carved by flowing water like the Grand Canyon on Earth. Instead, it appears to have formed when the Martian crust stretched and cracked long ago. The canyon system may have begun as a series of fractures caused by the swelling of the Tharsis volcanic region. But unlike similar features on Earth, Valles Marineris has remained largely unchanged for billions of years. On our planet, such a massive canyon would be constantly modified by erosion, earthquakes, and volcanic activity. New rock would fill parts of it. Shifting plates might close sections or open new ones. The canyon would be a living, changing feature. But on Mars, Valles Marineris has been preserved almost exactly as it was when it first formed, a fossil of ancient geological violence frozen in the Martian stone. This preservation of ancient features is one of the most striking characteristics of Mars. Because the planet lacks active geology, its surface serves as a museum of its own early history. Craters that formed billions of years ago still mark the landscape, barely changed by time. River channels carved by flowing water in Mars' distant past remain clearly visible, even though no water has flowed in them for eons. Scientists treasure this preservation because it allows them to study processes that happened early in Mars' history. On Earth, our active geology constantly erases and rewrites the record of the past. Old surfaces are recycled into the mantle. New rock covers old features. The planet's active systems keep the surface relatively young and fresh. But Mars remembers everything. Its silent stone holds the memory of ancient impacts, forgotten rivers, and long-dead volcanoes. The planet's stillness has turned it into a vast archaeological site where scientists can read the stories of geological processes that ended billions of years ago. This geological silence has profound implications for life. On Earth, our active geology plays an important role in maintaining conditions suitable for life. Volcanoes release water vapor and carbon dioxide into the atmosphere. The movement of tectonic plates helps regulate the planet's temperature over long periods. The recycling of rock through the mantle helps maintain chemical cycles that support life. Without these processes, Mars has gradually become less hospitable to life as we know it. Its atmosphere has thinned. Its surface has become dry and cold. The chemical cycles that might have supported early life have broken down. The planet's stillness, while preserving its ancient history, has also led to its transformation into the barren world we see today. Yet in this silence, there is a strange beauty. Mars stands as a testament to the geological forces that once shaped it. Its sleeping volcanoes and ancient canyons tell stories of a more active time. The The planet's stillness gives it a timeless quality, like a cathedral where the echoes of ancient activity still whisper through the rust-colored stone. As you prepare for sleep tonight, think about this quiet world spinning through space above you. Mars teaches us to appreciate the constant motion and change that makes Earth vibrant and alive. Its silence helps us understand how precious and rare our planet's ongoing geological symphony truly is.
But could that silence ever be broken? Could the sleeping giants of Mars ever stir again?
The question that captures the imagination of scientists and dreamers alike is whether human ingenuity might someday find a way to wake a sleeping planet from its billion-year slumber. In the quiet hours when most people sleep, scientists and engineers dream impossible dreams. They imagine machines that could restart the heart of a planet. They sketch plans for technologies that could wake Mars from its billion-year slumber. These are not the fantasies of science fiction, but serious proposals based on real physics and engineering principles. The challenge is enormous. To restart plate tectonics on Mars, you would need to reheat the planet's interior. You would need to melt the solid rock in its mantle and core, creating the convection currents that drive geological activity. This would require adding tremendous amounts of heat to a world that has been cooling for billions of years. One of the most ambitious ideas involves building nuclear reactors deep inside Mars. These would not be ordinary power plants, but massive heat sources designed to warm the planet from within. Imagine drilling deeper into Mars than anyone has ever drilled into Earth, reaching down through miles of solid rock to place artificial suns in the heart of the planet. These nuclear furnaces would need to be incredibly powerful. They would burn for thousands of years, slowly adding heat to the Martian interior. The energy required would be staggering, far more than humanity currently produces on Earth. But over geological time scales, even artificial heat sources could begin to stir the sleeping currents in Mars' mantle. Another approach would work from the surface. Giant mirrors, each 1 mile across, could be positioned in orbit around Mars. These mirrors would focus sunlight onto specific regions of the planet's surface, creating concentrated beams of solar energy. Think of using a magnifying glass to focus sunlight, but on a planetary scale. The focused starlight would heat the Martian surface to incredible temperatures. Over time, this heat would conduct downward through the rock, gradually warming the interior. It would be like slowly heating a large stone in an oven, waiting for the warmth to spread from the outside toward the center. Some scientists have proposed even more creative solutions. They imagine networks of deep drilling sites across Mars, each one equipped with systems to inject hot liquid into the planet's interior. These artificial hot springs would carry heat deep into the Martian crust, helping to warm the cold rock below. The liquid could be water heated by nuclear reactors, or even molten metal that would stay hot for long periods underground. Each injection site would be like acupuncture for a planet, placing sources of heat at strategic points to stimulate the flow of energy through Mars' interior. Another fascinating idea involves using the planet's own materials against it. Mars contains radioactive elements just like Earth does, but they are spread thin throughout the rock. What if we could concentrate these materials? Mining operations could extract uranium and other radioactive elements from Martian rocks, then bury them in concentrated deposits deep underground. These artificial radioactive deposits would generate heat through natural decay, creating warm spots in the planet's interior. It would be like planting seeds of warmth that would grow and spread over millions of years. The heat they produce would be natural, using the same radioactive decay that still warms Earth's core today. The most patient approach might involve simply waiting and adding small amounts of energy over very long time periods. Even modest heat sources, maintained for millions of years, could eventually begin to warm a planet's interior. This would be engineering on the time scale of geology itself, a project that might take longer than human civilization has existed. Each of these approaches faces enormous challenges. The energy required would dwarf any engineering project humans have ever attempted. The time scales involved would span many human lifetimes. The cost would be beyond anything ever imagined. Yet none of these obstacles violate the laws of physics. The ideas are ambitious, but not impossible. If any of these approaches succeeded, the changes would begin slowly. The first sign might be tiny tremors deep in the Martian crust, barely detectable even with the most sensitive instruments. These would be the planet's first geological size in billions of years, the stirring of stone that had been still since before complex life evolved on Earth. Over thousands of years, the tremors would grow stronger. Small amounts of molten rock would begin to move through cracks in the crust. Ancient fault lines might shift slightly, releasing stress that had been building for eons. The planet would slowly remember how to move. Eventually, if enough heat were added for long enough, true convection currents might begin to flow in the Martian mantle. Hot rock would start to rise from deep inside the planet, while cooler rock sank back down. The circulation patterns that drive plate tectonics would begin to establish themselves in the previously still interior. The surface changes would be subtle at first. Perhaps a few small volcanic vents would open, releasing the first new lava Mars had produced in millions of years. These would be tiny compared to the ancient volcanoes that already dot the landscape, but they would represent something profound, a planet coming back to life. Over millions of years, if the heating continued, Mars might develop true tectonic plates. The planet's crust would begin to crack and separate. New seafloor would form in the growing cracks. The ancient, preserved surface would finally begin to change and renew itself. The implications would extend far beyond geology. A geologically active Mars might be able to maintain a thicker atmosphere. Volcanic activity would release water vapor and carbon dioxide that had been locked in the rocks. The planet might even develop a magnetic field again, as currents began to flow in its reheated core. Such a transformed Mars would be a very different world from the cold, silent planet we see today. It would be a world where the ground occasionally shook with earthquakes, where new mountains grew and old ones were worn away, where the surface renewed itself through the constant recycling of rock. But all of these changes would happen on time scales that challenge human imagination. The engineers who started such a project would never see its completion. Neither would their children, or their children's children. It would be a gift to the far future, a project undertaken not for immediate benefit but for the long-term transformation of an entire world. As you rest tonight, consider these dreams of planetary awakening. They represent humanity's greatest engineering ambitions, the desire to become gardeners not just of Earth, but of entire worlds. Whether such projects will ever be attempted remains unknown. But the fact that they are even possible reminds us of the power of human imagination and determination. The question that follows naturally is how we might take the first small steps toward such an enormous goal. What technologies and methods might allow us to begin the slow process of warming a cold world? The first steps toward awakening Mars would be gentle ones. Like warming cold hands by breathing on them softly, the initial attempts to heat a planet would start small and patient. Engineers dream of technologies that could begin this slow dance of warming, each one adding tiny amounts of energy to a world that has been cooling for eons. Imagine vast mirrors floating in the space around Mars, each one the size of a city. These orbital mirrors would catch the light of the distant sun and focus it into concentrated beams. The beams would paint spots of warmth on the Martian surface, like sunlight focused through a magnifying glass, but gentle enough not to damage the ground below. These mirrors would not create the intense heat needed to melt rock instantly. Instead, they would warm specific areas of the planet just a few degrees above the normal temperature. Day after day, year after year, these warm spots would slowly conduct their heat downward through the rock, like warmth from a heating pad gradually spreading through a cold bed. The mirrors would need to be enormous and precisely controlled. They would orbit Mars in carefully planned patterns, ensuring that the focused sunlight moved across the surface in slow, systematic ways. Some areas would be warmed for months at a time, while others would be allowed to cool, creating temperature differences that would encourage the flow of heat through the planet's interior. Meanwhile, on the surface of Mars, drilling operations would begin their own patient work. These would not be ordinary drills, but specialized machines designed to bore deeper into a planet than humans have ever drilled before. Each drilling site would be chosen carefully, positioned above areas where the Martian crust is thinnest or where ancient geological activity suggests the interior might be more receptive to warming. The drills would work slowly, grinding through mile after mile of solid rock. The process would take years for each hole, but eventually they would reach depths where the rock is naturally warmer. At these depths, the drilling crews would install systems to pump heated liquid into the surrounding stone. This liquid could be water heated by small nuclear reactors or synthetic fluids designed to carry heat efficiently. The heated liquid would flow through networks of pipes buried deep in the rock, creating artificial hot springs far below the surface. These underground heating systems would work like the radiant heating in some homes, warming the surrounding rock gradually and evenly. Each drilling site would be connected to others through underground heating networks. Gradually, a web of warmth would spread through the Martian crust, creating zones where the rock is slightly warmer than it has been for billions of years. These warm zones would be too small and gradual to cause dramatic changes, but they would represent the first artificial steps toward planetary reheating. Some of the most interesting warming techniques would use Mars' own materials. The red planet contains metals and minerals that could be converted into heat sources. Iron extracted from Martian soil could be processed into specialized compounds that generate heat when they react with other materials. These chemical heat sources could be buried at various depths, creating long-lasting sources of warmth that would continue working for decades without maintenance. Another approach would involve capturing and concentrating the radioactive elements that already exist scattered through Martian rock. These elements naturally produce small amounts of heat as they decay. By mining them and concentrating them into deposits buried deep underground, engineers could create artificial radioactive heating systems that would warm the surrounding rock for thousands of years. The key to all these approaches would be patience and coordination. No single heating method would be powerful enough to warm an entire planet quickly. But multiple methods working together over very long periods could begin to create measurable changes in the temperature of Mars' interior. Scientists would monitor the effects carefully. Networks of sensors buried at various depths would measure tiny changes in temperature and detect the first signs of geological stirring. These measurements would be so precise that they could detect temperature changes smaller than a single degree, tracking the slow spread of artificial warmth through the planet's interior. The first signs of success might be almost imperceptible. Instruments might detect tiny shifts in underground rock, movements so small they would be measured in fractions of inches. Ancient stress patterns in the Martian crust might begin to relax slightly as the rock warmed and expanded. Deep underground, pockets of water ice might begin to melt, creating small amounts of liquid water for the first time in millions of years. Over centuries, these small changes would accumulate. The zones of artificially warmed rock would gradually expand, connecting with each other to create larger areas of elevated temperature. The heating systems would be continuously upgraded and expanded, with each generation of technology adding more efficient ways to transfer energy into the planet's interior. The entire process would require coordination across multiple human lifetimes. The people who began the project would never see its final results, but they would be able to observe the first signs that their work was having an effect. Temperature sensors would show gradual warming trends. Geological instruments would record the first tiny tremors as stress patterns in the rock began to change. This would be engineering on a scale never before attempted. It would require international cooperation, massive financial resources, and a commitment to projects that span many human generations. The people involved would be working not for immediate results, but for the long-term transformation of an entire world. Yet the basic physics is straightforward. Heat flows from warm areas to cold areas. Add enough heat to the right places for long enough, and even a planet-sized mass of cold rock will eventually begin to warm. The challenge is not whether it can be done, but whether humans can sustain the effort over the enormous time scales required. As you prepare for sleep, imagine this slow dance of warmth and stone playing out over centuries. Picture the patient machines working deep underground, the orbital mirrors painting spots of light across the Martian surface, the gradual accumulation of heat in rocks that have been cold since before life on Earth became complex. But what would happen when this patient warming finally began to take effect? What would be the first signs that a sleeping planet was beginning to stir back to life? After centuries of patient warming, something extraordinary would begin to happen deep inside Mars. The artificial heat sources, working tirelessly for generations, would finally reach a critical threshold. Like water that suddenly begins to boil when it reaches the right temperature, the planet's interior would start to show the first signs of reawakening. The changes would begin in the deepest places, where the added heat had been accumulating longest. Small pockets of rock, warmed beyond their melting point for the first time in billions of years, would begin to soften and flow. These would be tiny regions at first, no larger than rooms in a house, scattered throughout the Martian interior like seeds of geological activity waiting to grow. As these pockets of molten rock formed, they would become lighter than the solid stone around them. Following the ancient laws of physics, they would begin to rise, moving upward through the planet's interior with the patience of deep time. This rising motion would be almost imperceptibly slow, taking decades or centuries to travel just a few miles through the solid rock above. But movement, however slow, would be significant. For the first time in geological ages, currents would begin to flow inside Mars. These would be the planet's first tentative attempts at convection, the process that drives all geological activity on active worlds like Earth. The sleeping giant would be taking its first shallow breaths. Meanwhile, the slow heating would have other effects throughout the Martian interior. Ancient pockets of frozen water, locked in the rock for millions of years, would begin to melt. This newly liquid water would find its way into cracks and fractures in the stone, creating underground rivers and lakes that had not existed since Mars was young. Some of this water would carry dissolved minerals, creating underground hot springs deep within the planet. These hidden geothermal features would add their own warmth to the artificial heating systems, creating feedback loops that would help the reawakening process along. The planet would begin to contribute to its own revival. The first visible signs of change would appear at the surface. Scientists monitoring Mars would notice tiny increases in the planet's internal heat signature. Sensitive instruments would detect minute amounts of water vapor escaping from ancient volcanic vents. These would be the planet's first exhalations in eons, barely detectable whispers of the stirring activity below. In areas where the artificial heating had been most intense, small amounts of new volcanic activity would begin. These would not be the massive eruptions that built Olympus Mons in Mars' ancient past. Instead, they would be gentle seepages of molten rock, creating small lava flows no larger than streams. But they would represent something profound, new rock forming on Mars for the first time in millions of years. The planet's surface would start to show subtle changes. Ancient impact craters, preserved unchanged for billions of years, would begin to show signs of modification. Tiny amounts of erosion and weathering would start to alter their perfectly preserved edges. The geological museum that Mars had become would finally begin to update its exhibits. Sensitive seismometers placed across the planet's surface would record the first Mars quakes in geological ages. These would be incredibly small tremors, barely detectable even with the most advanced instruments. But they would mark a turning point in the planet's history, the return of internal forces strong enough to move solid rock. The tremors would start deep underground, where expanding pockets of heated rock would create tiny fractures in the surrounding stone. These fractures would propagate upward through the crust like slow-motion lightning, sometimes taking years to travel from their deep origins to the surface. When they finally reached the surface, they would create the smallest possible earthquakes, movements measured in fractions of inches. But even these tiny movements would be significant. They would represent the first steps toward true tectonic activity, the first signs that Mars might someday develop moving plates like those that shape Earth's surface. The ancient, rigid crust that had been locked in place for billions of years would be showing the first signs of flexibility. Underground, the changes would be more dramatic. Networks of artificial heating systems would create zones where the rock was warm enough to flow like thick liquid. These zones would gradually expand and connect, forming the beginnings of convection cells in the Martian mantle. Hot rock would rise in some areas while cooler rock sank in others, establishing circulation patterns that had not existed since the planet's youth. The process would accelerate gradually. As more rock began to flow, it would carry heat more efficiently from the deep interior toward the surface. This would help spread the warming effect beyond the areas where artificial heating systems were installed. The planet would begin to transport its own heat, amplifying the effects of the human-built warming systems. Ancient fault lines, dormant for billions of years, would show the first signs of renewed activity. These would be stress fractures in the crust where the rock had been stretched or compressed long ago. As the interior warmed and expanded, these old wounds in the planet's surface would begin to shift and adjust, releasing tension that had been building for geological ages. The atmospheric effects would be subtle but measurable. Increased volcanic activity would release small amounts of water vapor and carbon dioxide into Mars' thin atmosphere. These additions would be tiny compared to the planet's atmospheric needs, but they would represent the first steps toward atmospheric thickening. Mars would begin to exhale the gases that had been locked in its rocks for eons. Scientists would monitor these changes with a mixture of excitement and careful analyses. Every tremor, every wisp of volcanic gas, every tiny increase in surface temperature would be recorded and studied. The data would show whether the warming efforts were succeeding in their ultimate goal, teaching a dead planet to live again. The changes would be so gradual that they would span multiple human generations. The people who had started the warming projects would see only the earliest signs of success. Their children and grandchildren would witness the first real stirrings of geological activity. The full transformation would take thousands of years to complete. Yet each small change would build upon the others, creating a cascade of effects that would gradually transform Mars from a geologically dead world into something more dynamic. The planet would be learning to move again, remembering the geological processes that had once shaped its surface in the distant past. As you rest tonight, imagine this slow resurrection playing out across the centuries. Picture the first wisps of steam rising from Martian vents, the first tiny tremors shaking instruments scattered across the red planet's surface. A world would be taking its first tentative steps back toward geological life. But what would this reawakening world sound like? What music would a planet make as it learned once again to sing the ancient songs of moving stone and flowing rock? As Mars slowly awakens from its geological slumber, it would begin to create sounds that have not been heard for billions of years. If you could somehow listen to the planet's interior with perfect hearing, you would discover that a living world makes music. Every geological process creates its own notes and rhythms, combining into a planetary symphony that tells the story of forces moving deep below the surface. The deepest bass notes would come from the largest movements. As convection currents finally begin to flow in the Martian mantle, vast masses of rock would shift and circulate in patterns thousands of miles across. These movements would create vibrations so low in pitch that human ears could never hear them directly. They would be the fundamental baseline of planetary activity, the deep harmonic foundation upon which all other geological music rests. These bass notes would take centuries to complete a single cycle. Like the longest, lowest notes of a massive pipe organ, they would resonate through the entire planet. The rock itself would become a musical instrument, conducting these deep vibrations from the core to the surface. Sensitive instruments would detect them as subtle rhythmic pulses, the heartbeat of a world learning to live again. Above this fundamental bass, other frequencies would begin to join the composition. As pockets of molten rock rise through the mantle, they would create medium-pitched tones, like the middle strings of a cosmic cello. Each rising plume of hot rock would generate its own signature sound as it moves through the solid stone around it, creating melodic lines that weave through the deeper bass rhythms. The percussion section of this geological orchestra would come from more sudden events. As pressure builds up in underground chambers of molten rock, it would eventually be released through small volcanic eruptions. Each eruption would create a sharp, brief sound like a distant drum beat. These volcanic percussion notes would be scattered throughout the composition, marking moments when the planet's internal pressure finds release through its surface. Even the smallest geological events would add their own delicate sounds to the symphony. Tiny fractures forming in the rock would create high, crystalline notes like wind chimes made of stone. As ancient stress patterns in the Martian crust finally relax and adjust, they would release soft sighs and whispers, the sound of rock settling into new positions after billions of years of rigid stillness. The movement of underground water would add flowing melodies to the composition. As ice melts deep within the planet and begins to flow through networks of cracks and caverns, it would create liquid music. Some of these underground streams would gurgle and babble like hidden brooks. Others would rush through larger chambers like subterranean rivers, adding their water songs to the planet's growing symphony. Geysers and hot springs, if they eventually formed, would contribute their own distinctive sounds. Steam escaping from underground chambers would create soft hissing notes, like the gentle release of pressure from a cosmic tea kettle. Hot water bubbling up through surface vents would add rhythmic pulsing sounds, marking time like a geological metronome. The winds above the surface would interact with these geological sounds in fascinating ways. As warm air rises from newly active volcanic areas, it would create its own atmospheric music. The thin Martian atmosphere would carry these thermal updrafts across the landscape, adding wind instruments to the planet's orchestra. The sounds would be subtle, like breath moving through the pipes of a massive organ made from the entire planet. Different regions of Mars would contribute different instruments to this planetary symphony. Areas where the artificial warming had been most successful would play more active, complex melodies. Regions that remained geologically quiet would provide spaces of silence between the musical phrases, like the rests in a written composition that give meaning to the notes around them. The tempo of this music would be unlike anything humans normally experience. The fastest rhythms would unfold over days or weeks. Most of the melodies would take months or years to complete a single phrase. The deepest bass notes would require centuries to finish their cycles. It would be music composed in geological time, requiring enormous patience to appreciate fully. Scientists monitoring the reawakening planet would need special instruments to translate these sounds into frequencies humans could hear. Computer programs would compress the timescales, speeding up the geological music so that centuries of activity could be heard in minutes. The deep bass notes would become audible as low rumbles. The medium-pitched melodies would sound like slow, haunting musical phrases played on instruments made of stone and fire. As the warming project continued over many generations, this planetary symphony would gradually become more complex and rich. New instruments would join the orchestra as different types of geological activity began. The simple, sparse melodies of early reawakening would evolve into more elaborate compositions as the planet's interior became more active and dynamic. The music would tell the story of Mars' transformation. Scientists would learn to read the geological health of the planet by listening to its sounds. A healthy, active world would play complex, harmonious music with many different instruments contributing to the composition. A geologically sick or dying world would have a sparse, simple soundtrack with only a few lonely instruments playing isolated notes. Eventually, if the warming project succeeded completely, Mars might develop its own version of the complex symphony that Earth plays continuously. Our planet's geological music includes the deep bass of mantle convection, the percussion of earthquakes and volcanic eruptions, the flowing melodies of underground water systems, and the wind instruments of atmospheric circulation driven by surface temperature differences. But Mars' symphony would be unique, shaped by the planet's different size, composition, and history. Its music would include harmonies and rhythms that Earth has never played. Some instruments in the Martian orchestra would be completely new, created by geological processes that exist only on worlds that have been artificially reawakened after billions of years of silence. The people working on the warming project would become the conductors of this planetary orchestra, adjusting their heating systems and drilling operations to encourage different types of geological activity. They would be composing music on a scale never before attempted, using an entire world as their instrument and deep time as their recording medium. As you rest tonight, imagine this slowly growing symphony playing out across the centuries. Picture the first tentative notes being added to Mars' long silence, the gradual building of complexity as more geological instruments join the planetary orchestra. A dead world would be learning to sing again, creating music that no planet in our solar system has ever performed before. But ultimately, this growing symphony would be more than just beautiful music. It would represent the transformation of two worlds dancing together in the cosmic night, each one unique, each one contributing its own voice to the larger harmony of planetary life. Tonight, as you settle into the quiet comfort of your bed, take a moment to feel the gentle miracle beneath you. You are resting on a living world, a planet that breathes with the slow rhythm of geological time. Beneath your feet, stone flows like thick honey through the Earth's interior. Continents drift like sleeping giants across the surface. Mountains rise and valleys form in the patient dance of deep time. This dance has been going on for billions of years. Long before the first life stirred in ancient seas, Earth was already moving and changing. The same forces that carry you on your nightly journey around the sun also carry the very ground you sleep upon on its own slow migration across the planet's surface. You are a passenger on multiple journeys, traveling through space on a world that is itself constantly traveling and transforming. High above you in the night sky, Mars hangs like a distant red lantern. From your window, it appears as just another point of light among the stars. But now you know its story. You understand that this quiet neighbor was once more like Earth, with moving plates and flowing lava and perhaps even ancient oceans. Mars danced the geological dance for millions of years before its smaller size allowed the inner fires to cool and the music to fade to silence. Yet in that silence lies possibility. The same laws of physics that drive Earth's geological engine could, with enough patience and energy, be applied to wake Mars from its long slumber. The dreams of scientists and engineers, the vast mirrors and deep drilling projects, the nuclear furnaces and artificial hot springs, all represent humanity's growing ability to work with planetary forces on a geological scale. If those dreams ever become reality, Mars would slowly learn to dance again. Its first steps would be tentative and small. Tiny tremors would mark the beginning of new geological movement. Small volcanic vents would release the first new rock the planet had created in millions of years. Underground, currents of molten stone would begin their ancient circulation patterns, carrying heat from the deep interior toward the surface. Over thousands of years, these small changes would grow into something more dramatic. True tectonic plates might form, dividing the ancient Martian crust into moving pieces. New mountain ranges could rise where plates collided. Fresh ocean basins might open where plates pulled apart. The planet that had been frozen in geological time would rejoin the dance of worlds that change and grow and renew themselves. The two planets would then share something profound. Earth and Mars would both be worlds where stone moves and flows, where the surface is constantly renewed by forces rising from deep within. They would be geological partners in the cosmic dance, each one unique but both alive with the same fundamental processes that shape living worlds. From space, the differences would be subtle but significant. Earth would continue its ancient patterns, the dance it has been performing for billions of years. Mars would be learning new steps, developing its own version of geological activity shaped by its smaller size and different history. The red planet's dance would be slower and more gentle than Earth's, but it would be real movement after eons of stillness. The sounds of the two worlds would create a harmony unlike anything in our solar system today. Earth's complex geological symphony, with its deep bass notes of mantle convection and sharp percussion of earthquakes, would be joined by Mars' simpler but growing composition. The red planet would contribute its own melodies to the cosmic music, sounds that no world has made for billions of years. Future generations of humans might live to hear both planets singing their geological songs. Children born on Earth would grow up knowing that their world moves and breathes beneath their feet. Children born on a reawakened Mars would feel their planet's first tremors, witness its first new volcanic eruptions, and know that they were present for one of the most remarkable transformations in the history of our solar system. The partnership between the two worlds would extend beyond geology. A geologically active Mars would be better able to maintain an atmosphere and regulate its climate. The volcanic activity would release water vapor and carbon dioxide that had been locked in the rocks for eons. The moving plates would help recycle these gases, maintaining the chemical cycles that support more complex environmental systems. Such a Mars might even be able to support liquid water on its surface again. The thicker atmosphere created by renewed geological activity could trap enough heat to allow ice to melt. Rivers might flow for the first time in billions of years. Lakes could form in low-lying areas. The red planet might slowly transform into a world of red rock and blue water, a unique combination that exists nowhere else in our solar system. But even if Mars never truly awakens, its silent presence teaches us to appreciate the remarkable world we call home. Earth's geological activity is not guaranteed forever. Our planet's inner fires will eventually cool, just as Mars did long ago. The dance of the continents will slow and eventually stop. The symphony of moving stone will fade to silence. Until that distant time, we live on a world that moves and changes and renews itself constantly. Every mountain, every valley, every grain of sand has been shaped by the slow dance of geological forces. The ground that supports your house has traveled vast distances over deep time. The atoms in the rocks beneath your feet have been recycled through the Earth's interior many times, forged and reforged in the planet's deep furnaces. As you drift toward sleep tonight, rest in the knowledge that you are cradled by forces older and more powerful than human imagination can fully grasp. You are part of a living world, a planet that dances through space and time with the patient rhythm of geological change. Whether Mars ever joins that dance remains to be seen, but for now, you can sleep peacefully on a world that moves and breathes and dreams in the language of stone and fire and deep time. Sweet dreams on this moving world, where even the rocks beneath your pillow are slowly flowing toward tomorrow.